Okay, so today we start a new section, and the section is all about CNNs, residual nets. There's a bunch of exercises where we make our own modules, train them, and implementing convolutions and residual uh, connections. And there are a bunch of bonus exercises as well. So, so in this video, let's try to finish section 1 and subsection 1 and subsection 2. So we'll try to finish until convolutions. Okay, so let's begin. We'll run the setup. Yeah, I think I have an idea of what we can do with the module class. So let's go ahead and implement this. We'll be implementing rectified linear units, has no arguments. Just need to implement the forward method. Documentation is defined as element-wise maximum. Makes sense. Okay, so yeah, guess we just return max of x comma 0. Let's see. Will this work? Yeah, but I'm not sure if I should modify x or if it's okay. See how they have done it. Oh, this torch maximum, which makes more sense. I would like to do this. I do not want to modify X. Let's do that. Hmm. I was hoping it would cast it, but apparently not. Okay, now we implement our own linear module. We weight matrix and an optional bias vector. Okay, they're initialized from this distribution, a uniform distribution over this interval. This is the number of inputs. The intuition is that keeps the variance of the activations at each layer constant. I would like to go through this, but maybe after implementing the linear module. So yeah, remember I should define the weights in the init block. Make sure not to not mix up bias and self-taught bias. Hmm. So we store it needs to be a parameter. It's from a uniform distribution, right? How do I get the uniform? Is there a, let's go to docs. Yeah, yeah, we need to do this. So distributions, uniform, where low is -1 divided by features. and high is positive. The positive term of it. And now predefine bias. Bias, I guess, can be, or it should be named a specific way. Uh, guess then I'd have to do this. Hmm. And I want the shape to be yeah. Uh, yeah. If bias else none. And forward. Guess the representation would be to um, yeah, I guess it's useful to store Sorry, what was the issue? Not uniform. Oh, okay. Think I need to do this. Uh, okay. Hmm. I guess they want to do it the other way around. In which case, I need to change this. Uh, hmm. Hmm. Let's see how they have done it. Storing everything, and then it's a scaling factor. Okay. The input could have multiple dimensions leading up to the input features. I would like to honor that this works. Yeah. Hmm. Okay. Yes, makes sense. So, oh, all right. Okay, so we have a start dimension and then dimension. If it's positive, leave it as is. If it's not positive, then take the offset so that it becomes a positive index corresponding to the negative index. Hmm. And okay, shape left is the tuple of all the length of dimensions to start them. Similarly, for shape right, you have the tuple of all the dimension lengths after end them. And in the middle, you want to put them in one dimension. So you take the product of all the dimension lengths in this range, and you finally do a reshape. And you concatenate these three tuples, and it's flattened along these dimensions. Makes sense. I'll just run this. Okay, let's see. Okay, we're almost done with the ones first module. Put them together, create a neural network. Linear followed by ReLU followed by linear. It's called MLP. 10 output dimensions. Softmax to turn them into probabilities. Pre-softmax, they're called the logics. Yeah, they're non-unique because first of all, softmax is translation invariant. That is, you add any constant to each of the xi's and the probabilities don't change. They just cancel out in this right-hand side. So that's, yeah, so that's one obvious reason. Yeah, okay, if you take log probabilities, they don't change. They're uniquely defined for a given probability distribution. All right, so this is our MLP. This is what we're going to implement. Okay, so we need a flattening layer. Then we need linear layer takes this many features, outputs this many. Does it have bias? Oh, I'm assuming it does. And then you have relu. Yeah. And then we have another linear layer. And that's it. And we flatten input. We apply the linear layer, apply relu. Then we apply the final linear layer and then return. Let's see if this works. There are fewer parameters than expected. Why is that? Ha, my bad. Silly mistake. Yeah, let's look at the solution. Yeah, pretty much what we have done, but without the biases. Guess that's okay. All right, so that was the first module. Let's look at how to train these networks. Oh, okay, so we're defining a couple of transforms, converting them into tensors, and normalize each of these tensors. I guess this is the mean and this is the wait a minute, and that's the standard deviation. Okay. So a function get mnest takes the size for the training set, size for test set. We're loading them into this local folders and we're passing the transforms, creating the subsets, returning them. All right. Creating through two data loaders with path size 64. Hmm. We're looking at the first patch and we're looking at the first data point in the test set. All right. So it contains data sets, architectures, common transformations. So why do we have data normalization function? Uh, if we don't, then I guess the jumps are more uh, uniform in all directions. We have a gradient descent. Yeah. So if you have a normalized data, gradient descent is could take long time to converge if you end up in a flat region. And yes, of course, numerical issues are avoided if you keep the number small. So why do we have to shuffle the data loaders? It's possible, or there's some dependencies across the images if you take them in the order that they're stored. And if you want to break them and learn, uh, get a truly random uh, signal that's representative of the whole distribution, then it makes sense to do shuffle, I guess. Hmm. So TQDM, I'm sorry, finally device, we've seen this. Make sure tensors are in the same device. Uh, so we'll modularize the training loops later. Define batch size, we define the number of epochs. For each epoch, we go through the data loader, move them to device, find the cross entropy loss. Backward step, zero the gradients, store the loss function, store the loss value. Yeah, and update the progress bar. Makes sense. Let's do it. Just look at the loss. Yeah, let's break down batch size. Okay, so we have cross entropy laws. We have n examples for each one. Cross entropy laws per example is negative log probability. Is that correct? Yeah. Probability the model assigns to class C for sample n. The probability that we assign to the correct class. Negative logarithm of that. So this is the cross entropy of distribution with respect to another. And in our case, if Q is the true distribution, where we know the right labels for each example, and P is the output of the model, then this it will become essentially this. And we have the functional cross entropy method, which expects unnormalized logits. I'm interested in this. Okay, 6.5 intuitions for KL divergence. Let's go through the summary. How much more surprised do you expect to be when observing that over distribution P? If you falsely believe the distribution is Q versus if you know the true distribution.
The cross-entropy loss is the dominant loss function used in machine learning classification tasks. The cross-entropy formula is relatively simple to compute. It's a summation of the true probability multiplied by the log predicted probability over all classes in the distribution. Although the formula can be described quite simply in one line of maths, it seems to come out of thin air, and it's not clear why this is the standard classification loss function. In this video, we'll go through the intuition of the cross-entropy loss, how it's derived, and why cross-entropy has become the stable classification loss. Let's start with the basic classification setup to motivate the approach, and let's forget about cross-entropy. Imagine we're given an image of an animal, and we want a network to predict which class the image belongs to from a fixed set of possible animal classes. The overall process is that we have an input image, a complicated nonlinear model parameterized by some weights, and some output class prediction. There are a lot of design choices for the model, and one of the most important ones is the form of the output. We could have something complicated, like a text decoder which generates a text of which animal class the image belongs to. Or we could have a simple approach, where the model outputs a number that say that yes, recognize which class is most likely, probability of 100%. Returning to the model setup, the input to the system is an input image xi, and the output is the probability distribution over the different animal classes, p of y given xi. If we assume, the real question is then, what would be the best loss function to ensure that the predicted distribution is close to the true distribution? If you've watched my previous video on the KL divergence, you'll ability distribute for further details on why this formula captures distances between probability distributions so well. Therefore, an intuitive loss function would be to minimize the KL divergence between the model and the true distribution. So if we expand the formula, we have an expression which, if we minimized, will bring our model distribution close to the true underlying one. We can also simplify this expression by basic log rules and turn the division inside the log into subtraction outside the log. We can then separate the two expressions into distinct summations and finally note that the first term does not depend at all on the parameters of the model, and in fact is just the entropy of the label distribution. So if we're minimizing this expression with respect to parameters theta, it's exactly the same as minimizing the second term, which might look a bit familiar as it's the cross-entropy formula we saw at the start of the video. So to quickly summarize, in this classification setup, our network is implicitly modeling the output probabilities over all classes. A natural loss function would then be to minimize the KL divergence between the model and the true distribution, but minimizing the cross-entropy loss is equivalent to minimizing the KL loss, and since the cross-entropy loss has a simpler form, it has become the standard classification loss. Let's quickly tie up some loose ends to handle some practical details. The first detail is that if we're claiming to model a probability distribution, then we have to make sure that our output is a valid distribution, namely that the at the end this into PMFs by assuming that they were and the idea of it seems natural as it's effectively a simple loss function which
Okay. This is an aside on direct classes. We have a lot of different parameters. Use direct classes to keep track of them. Okay. We will add a validation loop. So I guess we could use this. We can use this code. And let's have this loader. Um, yeah, and then I need to do Yeah, I think this should work. Let's see. Oh, let me do this. Oops. Went from point 0.1 to 0.079. That doesn't make sense. Uh, hmm. Think in that case, what are we passing to cross entropy? Hmm. Guess then shape is this, in which case I need to do, don't have to do this. Let's see now. Okay. This, guess I should rather do this. And yeah, guess I don't need them anymore. Let's see now. Hmm, that looks much better. From 10% to 92%. This makes sense. At the beginning, it's all random, so yeah, you're as good as guessing a class at random. So 1 out of 10 chance, and it quickly increased to 92%. Cool. Yeah, let's look at the solution. So that's section 2. We'll do section 3 and section 4. Uh, yeah, maybe tonight or tomorrow. Uh, Before we end this, maybe I just want to go through that. Yeah, let's just go through cross entropy laws for once. So, if you recall, for one example, if you want to measure the loss, it's basically the negative log uh, probability assigned to the correct class. And if you want to take the cross entropy loss over a bunch of examples, just take average of that. Oh, so and this is similar to KL divergence in the sense that if you take the model's probabilities as one distribution and the ground truth labels as a one hot vector, it's basically taking the KL divergence between these two probability distributions. Um, yeah, and if uh, and there's an interesting statement here. Yeah, KL divergence and cross entropy differ by an amount which is independent of our model's predictions. So minimizing cross entropy is equivalent to minimizing KL divergence. And I think we've seen this here. Where's that? Yeah. So if you expand KL divergence between the true probability distribution and the probability distribution as calculated by a model, yeah, substitute the definitions and expand it, separate out the terms. You can see this term does not depend on the parameters of your model. And if you just look at the uh, remaining term, what you have is the cross entropy loss um, for the model. And yeah, so I guess that makes sense. Yeah, I think we're good. We can stop